Hi, good evening. This week I'm going to show you a few graph algorithms. This is for my discrete structures course. This is the week where we go over graph theory. We talk about the terminology of graphs like nodes, vertices, edges, directed, undirected, weighted, unweighted. Then we go over a few algorithms related to them, like this time I'm going to do Prim's minimal spanning tree and Dijkstra's shortest path. I think I'm just going to work a few problems. I'm going to kind of make them up on the fly, so there might be a little downtime in the stream here as I kind of make the graphs, but that's part of doing the problems. So let me go over briefly what Prim's minimal spanning tree is. First of all, this one is used all the time in computer networking, like constantly used. The idea is if you had, let's say, each one of these vertices represents a switch or a router in a network. You know, it's what minimal spanning tree does is it ensures that there is some way to reach all the computers in a network. Now, this diagram that I drew here might represent what a typical home network might look like, with a central router or hub, and then maybe an auxiliary one, somewhere off in a different room. But it's kind of like this star formation. And so every single computer in this network is reachable from any other computer by one of these links. The problem is that if one of these links goes down, like if something cuts one of these links here, that cuts off this part of the network here. So in a more, let's say, industrial or business environment, you'd have redundant links set up. You would have multiple ways of reaching every computer. Now, if you ever tried this at home, if you ever took a hub or a switch and plugged in a couple of wires into it that all went to another hub or a switch, the home networking just goes crazy, right? It doesn't know what to make of having two wires going to the same place, or it may just shut down those ports entirely, right? But the professional stuff you can get, the stuff that costs a lot more, it's more expandable and more robust, it'll see these duplicate links here and it will calculate that maybe in order to get to this node right here, it doesn't need to use this one. It can use this one instead, right? So it basically, in software, kind of cuts off this one here. And then if some problem happens later on and this one gets cut, it'll reactivate this link here. Or another thing you can do is, and this is a more advanced networking topic, is it can do something like trunking, which means I can use these links redundantly and get more bandwidth going to one of those vertices or one of those nodes. But that's not what minimal spanning tree is for. Minimal spanning tree is for ensuring that every single node on the network is reachable from any other node, and to also handle these redundant links here. The minimal spanning tree really comes into play if, let's say, this is a 100 megabit connection and this is a gigabit connection. Obviously you should use this one whenever you can, but if this one goes down, you can switch back to this one here. So every time you plug in a piece of networking gear, these network switches and hubs go through a minimal spanning tree calculation, and they try to figure out what's the best way to reach all the computers using the fastest links possible. And then if one of those links goes down, it recomputes that and comes up with a new minimal spanning tree. So it's called a spanning tree because the network it comes up with spans all of the vertices in the graph, and it's called a tree because there's going to be no cycles anywhere. If I was to pick up this picture, let's say by this node right here, and let everything dangle down, there would be no links going back up the tree. So the question is, will this video be uploaded to the YouTube channel? Yes, as soon as I'm done with this, then YouTube will grind away at it, and it should appear on my channel probably within half an hour or so after I finish it. So that should be by about 7:30 my time. The other algorithm I'm going to do is Dijkstra's shortest path, and this one is used all the time again by all the mapping things that you use on your phone and computer to find the shortest route between point A and point B. This one has been around for a very long time, and it basically finds like I said, the shortest path. So I think we'll just get started. I'm going to do Prim's minimal spanning tree first. What I did was I just drew a network here. And so each one of these here could be a computer. Another thing that spanning tree is used for is, and this is actually kind of a contrived example, but let's say these are homes in a new neighborhood, and these are the roads connecting the homes. And what we want to do is run sewers between all of the homes. We want to make sure all the homes get connected by a sewer line, but we want to use as little pipe as possible. So maybe each one of these weights on the edges represents the distance or perhaps the cost of running that sewer line. Like, you know, even though it looks like this is a far distance and this is a close distance here, maybe, you know, this is through dirt and this is through rock, and so that's why this one costs a lot more in addition to being further away. So that could be another example of why you'd want to use spanning trees, to minimize the amount of resources needed to be able to connect all of these vertices together. So the way that this algorithm is going to work is, first of all, since we're going to touch each one of the vertices, it doesn't matter which one we start with. We could start with any single one of these, and we're going to, what we're going to do, well, let's just start with A. Okay, so we're going to start here at A. Actually, I'm going to color it in. So right there, we're going to start there at A. I think that's a bad color to use. How about this one? There. And so we've got this set of vertices now. We've got the set of, the only vertex now is A. And so what we do is we look at all of the edges that are emanating from that vertex. So that's this one going to D, and that's this one going to E, and this one going to B. So we've got three three edges to consider, and we look at the one with the least weight. So we got a 3, a 4, and a 5. So we're going to use 3. Okay, so that means we're now going to go down here. So now A and D are the two vertices in my spanning tree so far, and then let me color in, I guess I'll use this. I'm going to color in that edge there to indicate that that's the one that we used. Okay, and then next, we again look at all of the edges that are emanating from our set of highlighted vertices. So that's the one going to B, the one going to E, and then we don't have to look at this one anymore because we've already used it, and it's this one here. Okay, so we've got this one, and this one, and again we choose the one with the lowest weight, so that's the one with 4, so we'll choose to use that one, which means we're now using E in our tree. And again, we kind of just repeat until we run out of vertices. We look at all of the edges emanating from those 3 vertices. This one, the one there, the one, oops, sorry, the one there, the one there, and the one there. So which one should we use? Let's see. So we got one with 5, 3, 5, 4, and 6. I think we should use the one with 3. So we're going to use that one. And that means now this one is colored in. Okay, keep repeating. We got this edge, this one, this one, this one, and this one. I think we're going to end up using this one because it has a weight of 2. All right, and now we're going to look at this one, this one, this one, and this one. Okay, which one has the least? Well, actually, there's 2 that have the least. It's the one going from F to C and the one going from F to H. So in this case, it doesn't matter which one we use. The minimal spanning tree is going to be the same in both cases. So we could maybe flip a coin, we could choose randomly, or if you're a computer, you might just choose the one that appears first. Like, you know, we got C and H. C occurs first alphabetically, so you might choose that one. There's really no reason to choose one over the other. And again, you want to be a computer about this, which means, you know, as a human, I could look at the whole thing. I could look at the whole chart and go, okay, well, which one, like, aesthetically looks pleasing? A computer wouldn't do that at all. A computer would just go, pick one, and pick the easy one, and that's probably going to be C. All right, So again, we're going to look at all of the edges emanating from our tree. So that's this one here. And actually, all this time I forgot to include this one in our list of things to consider. So actually, there's quite a few. There's this one, this one, this one, this one, this one, this one. Basically, all the rest of them. All right. So basically, every edge that's emanating from all of the vertices that are part of our tree. So it's basically all of them. And the one that's least is this one right here. So we'll highlight that one. And so we keep going. So look at all the edges emanating from our tree. This one, this one, this one, this one, this one. Yep, all those. The one that's the least. Okay, this one here is the least. It's 3, but it's already going to two vertices that we've already put in our tree. So we're not going to consider that one at all. So actually, I guess you could say, even though we might look at these edges here, we wouldn't really consider them because they're going between vertices that are already in our tree. So I guess the one that's the least would be this one here. So really, actually, I'm sorry, we should back up. The only edge that I would consider is this one, right? Because it's going to a vertex that we haven't visited yet. Okay, so we'll highlight that. And then that's it. So we've highlighted all the vertices, and so we're done. And so our tree is the highlighted edges, those right there. Okay, and it's called a tree because there's no cycles anywhere. If I was to pick up this graph by any one of the vertices, all the edges would just be dangling down. Okay, so let's add up the weights of all of these. So we've got 3, 4, 3, 6, 2, 2, and 2. For a total of 7, 8, 9, 10, 16 plus 6 is 22. If I'm doing my math right, 16, yep, 22. That's our total weight, and that should be the smallest amount, 22. So I kind of want to do another one just so we get it down pat. So I'm just going to make one. Start connecting it up. Boom, boom. There. And there's actually no reason why some of these edges can't cross over each other. You know, if this is these are roads, then obviously there's a bridge there of some sort. If these are computer networks, then you just got wires crossing each other, and that's not a problem. So maybe I'll put one going over this way and one going this way. All right, and let's letter these: A, B, C, D, E, F, and G. And then I'll put in some weights. I don't know, is it 3, 4, 2, 3, 2, 4, 4, 1. Which one I haven't done yet? 3, 2, 5, and I think that's all. Looks good. So once again, we'll just start somewhere, and then we'll look at all of the edges coming out of it. And this one is the least. So that means we're going to B next. And we're going to use this edge. Okay. And again, so we look at all of the edges that are emanating from our tree, and I'll kind of revise this, that are all the edges emanating from our tree that don't go to vertices that are already in the tree. So I look at this one, this one, this one, this one, here, here, and the one across the top. We got a question: what if you find a better edge to an already visited node? shouldn't happen if you're doing this correctly. Since you're always going to take the one with the least weight, you couldn't find one that was better than that. I think the thing to do would be to see if you can come up with an example, specific example, and then like take my current graph here, and maybe if we change some of the numbers and we see what happens. Okay? All right, so looking at all of those edges, I think the one with the least weight, there's actually a couple possibilities. We could do this one or this one. Yep. So we'll just pick one, and I'll pick maybe the one with the least letter, or yeah, earliest letter. So that's this one. Okay. And now I look at all the edges coming out of that tree. And I wouldn't look at this one here because A and D are already used. This one, this one. Okay, so obviously you're going to pick this one, the one with the 1. Okay, now which edges do we look at? The one across the top, B to E, B to G, D to F, A to F. And the one with the least looks like D to F. So we pick that one. Now there's only a few more to look at. So again, across the top, A to E, B to E, B to G, F to G. So it looks like the winner is B to E. And then there's only a couple more to look at. B to G, E to G, and F to G. So we're going to take E to G. And that should be it. Okay, total weight is 1 plus 2 plus 2 plus 3 plus 2 plus 2. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total weight is 12 on that one. If I added that up correctly. Okay. I'm just double checking my work here. To 3 plus 2 plus 2 plus 2 plus 1 plus 2. 3 plus 2 plus 2 plus 2 plus 1 plus 2. Got it. So a total weight of 12 on that one. All right. So there's a way to actually, now, so this is obviously a graph done on visually. And so we, the human, are looking at the graph and we're figuring out which one is the least. But if you're a computer, you're not going to have the graph as a picture. You're going to have the graph probably as some kind of numerical representation. So let's do the same algorithm, but we're going to do it in a matrix form. So all of the numbers representing the graph are going to be there, but we won't have the picture to work with. And so let's see. What I need to do is, now, I'm kind of tempted to use this graph as the basis for my matrix, but the problem is that that's a lot of numbers to put in. So I think I'm just going to use a simpler one and go with that. All right, so let's see, how many vertices should I have on this? A, B, C, D, 5 vertices maybe? A, B, C, D, E. Let's go with one more, F and F. So the idea here is if a vertex is connected by an edge, we'll put a number at the intersection. So let's say if D and C are connected by an edge, there'll be a number right there to represent the weight of that edge. So let's put some numbers in here. Let's say A goes to B on 3, A goes to E on 2, and I need to duplicate those numbers down on the flip side. So B goes to A on 3, B goes to A goes to E on 2. Let me put in some lines here. There. Let's make B go to D on 1. So B goes to D on 1. Maybe B goes to E also on 3. See, since this graph is undirected, I have to put two numbers in, one from E to, let's say, E to B, and then one from B to E. Let's put in some more numbers. Maybe C goes to A on 4. So there's a 4 there. F goes to C on 2. And F goes to E on 3. And let's put in a few more. Maybe D goes to F? No. So yeah, I'm looking at this going, what would look aesthetically pleasing? How can I fill this in? And this is probably not the right way to randomly choose things. Let's see, let's put a 1 there. So that was D to C. So that means a 1 goes there. And I kind of feel like I want to put in one more number. See, now I'm looking at going, okay, all the nodes have 3 things coming out of it. Maybe I could put E has one more thing. Maybe E to D on 2 and 2. Okay, I think that's it's nicely filled in, right? That. Okay, so what we're going to do is we are going to, let's say we're going to start at A, just like we did before, just start arbitrarily. We can start anywhere, but a computer might start at A. And remember, in our graph over here, like we chose to start at A first, which means we immediately highlight it in, and then we never consider A again. All the highlighted vertices we never look at again. So we are essentially going to, so remember now, we've got A here, and we also have A here. Okay, so I'm going to color this a certain way. So I'm going to cross out A, because I never want to consider it again. But then I'm going to highlight this column. And these numbers, 3, 4, and 2, under B, C, and E, represent the 3 edges that are coming out of A. So A, we can go from A to B, C, or E, and then we should just pick the lowest one. I think it's obvious which one to pick. We'll pick that one. So that means we chose to go from A to E by following the 2 edge. That means that we should now cross out E, because we don't want to consider it again, but we're also going to add E to our list of vertices that are in the tree. So these vertices over here are the ones that are in the tree, and these are the ones we're crossing out. These are also in the tree, but we're crossing them out. So now we're going to look at all of the numbers that are highlighted that haven't been crossed out yet. So that's the 3, the 4, this 3, this 2, and this 3. These are now the 1, 2, 3, 4, 5 edges that are coming out of those 2 vertices, A and E. And we pick the lowest one, which is this one right here. We'll pick that one. So that means we chose to go from A to D by following the 2 edge. Therefore, we should cross out D and also highlight it over here. And then look at all the numbers that are highlighted. 3, 4, 1, 1, 3, and 3. Pick the lowest one, and if it's a tie, arbitrarily pick one of them. I'm going to pick this one just because B comes first. So we're going to cross out the B column and highlight the B row. And then look at all the highlighted numbers, 4, 1, and 3. And it looks like this is the winner right here. So we're going to cross out the C column, highlight the C row, and let's see, there's not much left. There's this one and this one. I think that's all. So we'll pick this one. Yep. So that means we chose to go to F. So we're going to cross out F. And just to be complete, because we're a computer, we're going to highlight F. And then we're going to see at this point, we've highlighted all of the vertices on the left-hand side, so we know that we're done. And so now, what edges were in our tree? Well, let's start at A. And then from A, we went to E. And then from E, we went to D. And then from D, we went to B and C. Like that. And I think, let's see, 1, 2, 3, 4, 5, we got one more. From C, we went to F. Like that. And I think that's all. 1, 2, 3, 4, 5, 6. That's all my vertices. And let's put in the weights. A to E had a weight of 2. E to D had a weight of 2 also. D to B had a weight of 1, and D to C had a weight of 1, and C to F had a weight of 2. And then we can just add those up, and that's our minimum. 2, 4, 5, 6, 7, 8. Total weight is 8. Okay, you want me to do another one like that? Go over that process again. Maybe, I'm thinking like, should I do one with more vertices, or I should do one that's a little more dense, like pack in those numbers more? Yeah, why don't we do one that's more dense, but about the same number of vertices? So A, B, C, D, E, F, A, B, C, D, E, and F. All right, let's say A to B on 3, maybe A to D on 4, A to E on 2, A to F on 2 again, which means I need to replicate those numbers down here, 3, 4, 2, and 2. Okay, how about B to C on 4, B to E on 3, B to F on 1. So let's see, 4, 3, and 1. Okay, C to D, 2, C to F on 2. Let's just go 2, 2, 2 on that one. 2, 2, 2. Let's put a 3 here. I'm just kind of randomly making up numbers. A 1. So that's 3 and 1. Well, E's really getting packed in. How about F? I can't do F to F, right? That would just be one pointing back to itself. That would never get used. So, I mean, you could, I guess, in your graph have a loop pointing back to itself, but since you'd immediately highlight that vertex, you never consider that edge, so it's kind of pointless to put one of those in there. How about a 4 here, which means there's a 4 there, and that'll be good enough. Okay, so this one has a lot more connections in it. Let's see what happens. So if you remember, we are going to start somewhere. We're going to start here at A, which means we're going to cross out the A column and also highlight it, and then look at all the highlighted numbers that haven't been crossed out. So 3, 4, 2, and 2. We have a tie between 2 and 2, so let's just pick one. Let's pick E. Oh, whoops, let me, circle that one. All right, so what am I doing? Oh yes, I am highlighting that one. Okay, so 3, 4, 2, 3, 2, 3, 4. We got a tie here and here, so I'll pick C. Whoops. Gotta remember to circle that. All right. Oh, it looks like we got lots of ties here. We've got 3, 2, 2, 2, 4, 3, 3, 4. There's 3 2s. So we'll just arbitrarily pick one. Maybe D. And which means let's see, I picked D, right? So that's right there. What do we got? 3, 2, 2, 4, 3, and 4. I got 2 2s. They're both going to F, so it doesn't matter which one I pick. I'll pick this one. Okay, so we cross out F, and we highlight it, and then we look what we got. 3, 4, 3, and 1. Looks like we should pick the 1. Okay, so that means we cross out that row, highlight that column, and that's the last one we've highlighted, and everything's been crossed out at this point, so we're done. And now we can figure out what our tree is. So we've got A going to E and F with weights of 2, and then E goes to C with a weight of 2, F goes to B with a weight of 1, B doesn't go anywhere, and then C goes to D with a weight of 2, and I think that's it. That is our tree. And the total weight is 4, 6, 8, 9. And that should be the minimal spanning tree. Okay. So what I've done is I've done 2 graphs visually doing the spanning tree, and I've done 2 of them using a matrix. And that should, I think, at least, as far as kind of illustrating to you how the algorithm works. Now, you can go online, you can go to Wikipedia, and you can find the algorithm spelled out step by step, and you can follow that along. But what I want to do is just kind of quickly go over it and show you how it's done so that you can do it yourself, rather than us stepping through an algorithm laboriously. Okay, so now let's do, this is Dijkstra's shortest path. And like I said at the beginning of this video, this is used all the time in like Google Maps and MapQuest in order to find the shortest path between 2 points, point A and point B. And actually what this algorithm is going to do is it's actually going to find the shortest path to all the points in the map, not just the beginning and end. So kind of a side effect of running the algorithm is it actually finds all of them. So let's make a very, very simple map. And I have one kind of planned out. A, B, C, D, and E. So there's my map, and each one of these vertices could represent a city, and then these lines represent the roads between them. Where's this algorithm actually use network routing? You're talking about the spanning tree, or you're talking about the shortest path? Shortest path, like I said, is used for mapping, and then spanning tree is used a lot in computer networking to make sure that every node in a network is connected to every other node by some route, by the cheapest route. So in this case, cheap might be speed, or it might be perhaps the cost of using that particular network connection, but most likely for the routers and switches, it's simply like the speed or the latency, how quickly you can get packets from one side to the other. Let me put in some weights here. So we'll go 4, 2, 1, 4, 1, 2, and 8. And what I want to do is I want to go from A to D. A is my starting vertex, and D is my destination. So I want to start at A, and I want to come out from D. And now, we as a human could just look at this graph and go, oh, I see what it is. It is, wait, it's not so obvious, is it? It's probably not that one, right? Because that has an 8 in it. Maybe it's this one here, that has an 8. Or, oh, here's a shorter one, that's 7, right? Or is that the shortest one? 4, 1, that can't be that. Maybe it's 2, oh, here, 2, 1, 4. Wait, no, that's 7 also. 2, 1, 2, 1. Oh, that's 6. That's the shortest path right there. Right, it actually took us a while. Took us a while to find the shortest one just visually, and it's not necessarily the one with the fewest vertexes. It's actually the one that you actually pretty much had to go through all of them to find that one. So let's see how the computer would do this. Okay, so the computer would maintain 2 sets of vertices, one called current and one called visited. So you can kind of picture this as you drop a stone into a pond, right? And the waves ripple outward, and there's basically going to be a set of vertices that are kind of on the wave front as these vertices come out, as this wave front comes out. So you might drop in your stone right here, and then it ripples out to this here, and it ripples out to this here. So these vertices that are on the wavefront are called your current. They're the ones you're currently considering. And then visited are the ones that are behind the wavefront. You never have to consider those again because you've already figured out the shortest path to those vertices. Okay, so what we do is we tentatively figure out, put in the weights to all the vertices, or the distances of all the vertices. So to get from A to A, it's a distance of 0. You just put in a 0. And since we haven't started the algorithm yet, you put in infinity for all the others. We don't yet know what the distance is to all those vertices, so we just say it's infinity. And now we're going to start the algorithm. So we're going to start here at A. A is our current. And we're going to traverse down each of the vertices, each of the edges to the neighbors of A. So that's 4 and 2. And then we'll update these tentative weights here if the new weight is lower than what we've got. So what we got here is infinity. 4 is less than that, so we're going to put a 4 here. And we're also going to write down where we came from to get there. Okay, so the distance to B is 4 so far, right here, and we came from A. Okay, we're going to need to write down those vertex names because when we find what the actual shortest path is, we're going to start at the destination and we're going to work our way backwards. So we have to keep track of where we came from so that we can find that shortest path. Okay, next we're going to go down here and we're going to update that to 2, again from A. And at this point, we have now looked at all of the neighbors of A. We know the shortest path from A to A. So this one, A, is now considered visited. We never have to look at it again. So I'm going to put A here on visited and cross it out from current, and I'm going to add in B and C to my current because they're the ones that are under current consideration. All right, so look at B and C, and look at their weights, their distances, 4 and 2, and pick the smallest one. So that would be C here. So I'm going to put a little arrow here next to C to indicate this is the one that under what we're actually looking at. All right, so now what we do is we traverse all of the edges emanating from C, and we update the distances to each one of those vertexes that are its neighbors. So that means we're going to update D to be this number 2 plus this number 8. And that comes out to be 10, and we came from C. Okay, so the distance, as far as we know, the distance to D is 10 if we came from C. So that's this route here. Okay, that's only one of the vertices. Let's now do this one here. So we take this number, 2, we add this number, we get 3, and that's less than this number. So we're going to change this one and say we have a new lower number, this one here, and it came from C. So we erase this one, this 4A, because that's longer. So there's a new shorter way to get to B, and that's through C. All right, let's see. At this point, I think we have found the shortest way to get to C, and that's from A. So we can now cross out C, add it to our visited list, and we're going to add on D to our current. And then let's look at B and D, this one, and this one, and we see that this one is the lowest. So we're going to look at B, put a little arrow there, and we're going to update the weights. All right, so 3 to E, let's see, 3 plus 2, that means this is 5 from B. And then we're going to look down here. So 3 plus 4 is 7, that's smaller. So we're going to go 7 from B. And that's it, right? So since C, we already went to C, we don't have to look at this route here, this edge. So that's it, I think, if I got this right. Yep, I've updated all of those. So I can now cross this one off, and I'm going to add E to our current. B is now done. So which one is, of our currents, D and E, which one has the least? It's this one here, this E. Almost 5. So now, some of you might be asking, like, well, once I reach D, like when I reach this number here, can I just stop? And now you can see the answer is no, right? Just because we found a distance of 10 doesn't mean that's the lowest one. That's why we have to keep going. So it's not sufficient to stop once you reach your destination node. You got to keep going until you eliminate all the other possibilities. So we found the 7B. Is that the lowest one? No, it's not. Actually, there's going to be one that's lower than that. So you can't stop, again, just because you reach your destination. But now we're doing E, which is this one right here. And let's see, we're going to update anything. So we go E. We don't have to look at this one because B is on our visited list. E to D. Let's see, that's 5 plus 1 is 6. That's lower than that. So we get to change that one. 6E. And that's all of the vertices that we haven't visited yet, right? We're not going to go back this way. We obviously can't go there or there. So we're done with E. We'll cross that one out, add it there. And the only remaining one to consider is our ending one, and there's nothing to do there, right? There's no more vertices that we can go visit. So now we can cross that one out, add this to our visited list, and we know that we're done. Okay, so what do we know about the graph now? We know that the shortest distance from A to D is 6. And what is that path? Well, you kind of trace things backwards. So to get to D, we came from E, so it's there. Let me use a different color. To get from D, and then E came from B, B came from C, and C came from A. So there's our path from A to D. Oops, how come? Oh, I see. I hit undo accidentally. There it is. Okay, so our shortest path is here. Boom, 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 boom. And it's not so obvious from just looking at the graph. It took a little, so kind of like by hand, I had to do a guess and check. I tried a route and then see if it was the least so far, and then I try another route and I try another route. We want to kind of eliminate this guess and check, guess and check, guess and check. So this is a very nice algorithm, and it's not really, it doesn't evaluate all possible routes because, as you saw, it finds the one with the least weight so far and goes from there. And so it's actually pruning the tree away kind of rather quickly. It's not the fastest algorithm. I mean, it's not, as far as algorithms go, it's not super duper fast, but it's reasonably fast. Should we do another one? Might as well. Got about 15 more minutes. So let's do one more. Why don't we, let's see, 1, 2, 3, 4, 5. Why don't we put in one more vertex? Let's label them A, B, C, D, E, and F. Let's put in that, and let's put in this one here, and then some weights. I'm blanking out, trying to come up with some numbers here. Let's put in some larger numbers like 10, 25. This could be actually like distances, right? 40, 10, 15, 12. Oh, now I'm actually trying to make numbers that'll work out well. 8. I'm terrible at picking random numbers. 7. Let's go 20 here. You know, usually, obviously, we're going to come up with some different. I'm trying to come up with numbers where we're always updating the values. Let's put another 10 there. And last but not least, let's put a 15 there. Okay. And let's see, where should I come from and where should I go? I don't have to start at A, and I don't have to end at D. Maybe we can do F to C, perhaps? Or we could do A to C, that's obvious, right? How about let's do F to C. We'll go F to C. All right. So this is where we want to start. This is where we want to come out. Okay, so we have current, visited. So our current is F. Oh, and we got to go in. Let's see, 0, infinity, 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 and infinity. All right. So we start. So we start here at F, our current, and we update the weights on A, E, and D. Everything is reachable from F. So this is 8, from F. This one is 15 from F, and this one is 40 from F. And that means this is now done, and I'm going to add A, E, and D to my current. And then I pick the least, 15, 40, and 8, so it looks like I'm going to pick this one. So I'm going to look at A next. All right. Sorry, I'm switching colors here. All right, so if we go to A to B, that means it's going to be 8 plus 10, which is 18. Oh, sorry, it's not B, that is A. Okay, and then A to E is 8 plus 25. 8 plus 25 is 33, and that is not lower than 15, so we're gonna keep this one. It's still better to go from F to E directly rather than go this way. And that's it. Those are the only two I have to look at. So I've updated all the weights from A, so I now know that the best way to get to A is following this one from F. So I can now cross out A from my current, add it to my visited, and I'm going to add B to my current. And now I look at all the currents, 18, 15, and 40, so I'm going to do E next. All right, so E back to B is 15 plus 10 is 35. That's not better than the 18, so we'll leave that one. And then E to D is 15 plus 10 is 25. That is better than the 40, so we'll change that one. What did I say that was? 25? 25E. And that's it, right? That's all I got to do. Those are the only two that are reachable from E that aren't already visited. F is visited and A is visited, so I don't have to look at those. So that means that E is done. And did I add anything to my current? D and B? Nope, I didn't. So current stays the same. All right, the lowest ones of those two, 25 and 18, is B. That's the one I'm going to look at now. So that's this one. From B to C is 18 plus 7, that's what, 25? 25 from B. And then I look at B to D is 18 plus 20 is 38. That's not better than the 25, so I'll leave that. And then I don't have to look at this one, don't have to look at this one because those are already my visited, so I'm not going to touch those. Okay, so that means B is done. And I added C to my current. And the least of these two, actually there's a tie. What should I do in the case of a tie? Should I just say I'm done, or should I look at D? Well, actually, I need to completely exhaust my current list here. So just because this one is, again, just because this one is chosen doesn't mean I should stop. So let's choose this one next because alphabetically it comes first, right? So we'll do C. That'll be my current. And then I look at all of the unvisited vertices from C. Well, B is visited, so I'm not going to look at that one. I'm going to look at this one. I go 25 plus 15, that's 40. That's not less than 25, so I'm not going to update that. So the question is, do I mark that one as visited because that's the best? I guess I do. Because, yeah, I think I do. So, whoops, this color here. So that means this one can be added there. And I think that means I'm done at this point, right? Because I've reached my destination vertex and I looked at all of its neighbors. So what about D? Well, obviously D had a weight of 25, and if I add 15 to it, that's not going to be any better. So I think at that point I can stop. I'm a little concerned. I'm not looking at any notes here, so I'm not entirely sure what to do about this case. We had a tie, and I arbitrarily chose my destination vertex. And yeah, I guess we're just going to stop. So basically, this algorithm stops, even though I haven't looked at all of the vertices. I didn't look at D, but I got to my destination and I marked it as visited. So I think I'm done. And so if D actually happened to have a smaller weight, like let's say this was 24, what would happen if this was 24? Then I would have picked this one first, and I would have tried to go here, and then I would have looked at C, and actually 24 plus 15 would have been 39. It's not lower, so I wouldn't have changed this weight over here. So I think I'm good. So as soon as I mark my destination vertex as visited, the algorithm is done. And so the route is from C to B, and then from B to A. So it's just across the top with total weight of 7, is that right? 25 to B, 18 to A. Got one more, and then down here. Yeah, there we go. So it's a total weight of 25 to get from F by this route over here. And notice, like I said earlier, it also calculates the weight to get to every other vertex from our starting vertex. All right, so the question is, how do I represent infinity in C? Well, you can't really represent infinity in C. So what you have to use is a number that's just bigger than any other number. So in C, if you go hash include, I think it's limits .h, then there should be a value in there called int underscore max that represents the largest int on your particular architecture. And on a 32-bit, it should be something like 2 billion something. So that would be what you would use instead of actually infinity. Or yeah, it's called int max. It's all capitals. Int underscore max. So the algorithm in human terms uses infinity, but if you actually implement this in a computer, you should use the largest number you could possibly have, or use some kind of special flag of some sort, like maybe, I don't know, this is probably not what you would do, but each one of these edges here, or each one of these vertexes here could be a struct, and the struct could be what am I saying? The distance to that vertex, where you came from, the name of the vertex, and also maybe a Boolean flag that says whether or not this is infinity or not. But what I would do is I would just set them all to int max and hope that you never have a weight of 2 plus billion somewhere in here. So one thing that the shortest path algorithm can't handle is if you had negative weight. So let's say one of these edges here had a weight of like -10, right? So basically every time you traverse it, it costs less than before. And so when you have negative weights in here, then what happens is you just want to use that edge over and over and over again, because every time you cross it, the number goes down a little bit. So it can't handle negatives. And then one of the questions that comes up is, how do I maximize the weight or the distance? In other words, how do I find the path from, let's say, A to C that uses the most resources? And you have to put a constraint on here. Obviously, you shouldn't allow cycles, right? Because if you allowed cycles, then you would just go around and around and around and use up more and more resources. What you want to do is find, let's say, the route through here that sort of is the longest possible without going through a vertex again. So you might go, well, it'll be this one here, and then this one, and maybe this one. So that's maybe 67. Or maybe to use the most amount, maybe go this way, and then this way, and then this way, and this way, and this way. That might use 40, 50, 75, 85, 92. That's one that uses a lot. So how do you maximize the weight? Well, I suppose one thing you could do is you could set all these tentative weights to 0, and then you're flipping the condition around. It's like if the distance you found is greater than the number you've got there, then you go ahead and update it. And of course, you don't want to go to any of the ones you visited before. But another way to do it without changing the algorithm at all is to just change the weights. So what you do is you find the reciprocal of all these weights. So you do 1/10, 1/7, 1/15, 1/20, 1/10, and so forth, 1/40. So you flip all the numbers over, and then you just find the minimal, the shortest path. And then that's also will happen to be the longest path. So you'd end up using all, like this one here, and this, and this, and this, and this, because all that all adds up to a very, very small number. The larger these weights, the smaller the reciprocal, and so you end up using those weights. So if you want to find the maximum distance, reciprocate all the weights, and then just find the minimum, and it works. So it's a very, very easy change to do that. So reciprocate, is that a word? Reciprocate all the weights, and then find shortest path. Okay, so what did I do today, just to summarize? So we talked about minimal spanning tree, which I said is used all the time in computer networking for ensuring that there is some way to reach all the computers or nodes or routers in the network, and also handle redundant links so that if one or more of these links goes down, the networking equipment just recalculates the spanning tree and figures out the best way to reach all the nodes from any other node. And then we also talked about shortest path, which is used all the time in mapping and navigation. Now, one of the things for like Google Maps, and honestly, I'm not a mapping expert, so I don't really know how it works for real. But obviously, for something like Google Maps, the number of vertices and the number of edges is just astronomical, right? Basically, every intersection on the map represents a vertex, and every road that's connecting those intersections represents an edge. And so there's just, if not millions, there's billions of vertices to consider, and some magnitude greater than that, edges to consider. And as we saw, Dijkstra's shortest path finds the shortest path between your starting vertex and all the other vertices in the map. And so clearly, for something like a map of the entire world, that's just too much to calculate. And so Google must have some other heuristics that it uses to make sure that it doesn't calculate everything. I can only guess what those heuristics might be, but it might be something like only consider roads that are more or less headed in the right direction, more or less. Or maybe it's like consider things like freeways and major roads first, and then look at things like side roads. But I've obviously got some way of finding the shortest path from point A to point B that doesn't calculate every single path through the entire world. Or maybe it's something like find paths that don't deviate from a straight line path by more than a few miles, or some fraction of the total distance from the starting and ending. I'm not exactly sure what it does, but clearly they do some extra work in there to minimize the amount of calculations they have to do. So I showed how to do the minimal spanning tree using a visual graph. And I also showed how to do it using a matrix. So if you were a computer program, this is how you'd represent your graphs, as a matrix, probably a 2D array. Did a couple examples of that. And then I did shortest path. I just did this one visually. I know there's a way to do it with the matrix, but I don't. For one thing, I haven't worked out an example myself, and the other is I'm kind of out of time. It's already been an hour. So I did a couple examples of that. So at this point, I think I'm going to sign off. We've been doing this for an hour. We worked through a couple of examples. I hope it cleared things up for some of you, and I hope it gave some of you a little bit more insight into how things like Google Maps and computer networking works behind the scenes. So I will see you all later. See you in class if you're in my classes. Otherwise, I'll see you online later on. And if you have any questions, go ahead and post them in the chat, and I'll do my best to answer them. I'll stick around for a few more minutes. So have a good evening. Goodbye. I'll see you later.